The longest bridge on Earth does not have a famous arch, a forest of cables, or two towers disappearing into the clouds. In fact, if you search for it online, there is a fair chance the dramatic photograph you find is of a completely different bridge. The real Danyang Kunshan Grand Bridge is quieter and much stranger. It is a double-track railway viaduct that repeats across eastern China for 164.851 kilometers. That is more than 102 miles of concrete, carrying high-speed trains between Danyang and Kunshan as part of the Beijing-Shanghai Railway. You cannot drive across it. It does not cross one enormous sea, and its record was not won with one impossible leap. It was won by refusing to return to the ground. At a constant 350 kilometers per hour, the length alone represents more than 28 minutes of travel. Beneath the train, the landscape changes from farmland to roads, canals, towns, and lake water, while the structure keeps repeating the same basic instruction: foundation, pier, beam. Foundation, pier, beam. That repetition sounds simple until one detail changes. The ground below is part of the Yangtze River Delta. It is soft, wet, and crowded with infrastructure. A high-speed train above it demands a track so smooth that tiny, uneven movements matter. The builders therefore had to mass-produce thousands of heavy structural elements, position them across one of China's busiest regions, and make the result behave like one precise railway. This is the real puzzle of the world's longest bridge. Not how China crossed a single obstacle, but why it decided that, for 165 kilometers, touching the ground was the bigger risk.
If you enjoy finding the engineering hidden behind record-breaking numbers, subscribe to Mega Projects. Because the first secret of this bridge is that its extraordinary length begins with an extremely flat landscape. Southern Jiangsu is part of the low Yangtze Delta. Rivers, drainage channels, and lakes divide fertile farmland, while roads, railways, and expanding cities compete for the remaining space. A railway designed for 350 kilometers per hour is less forgiving. Fast trains dislike sharp curves, sudden gradients, and uneven settlement. If one section of the ground sinks differently from the next, the railway develops a vertical change that a slow freight train might tolerate, but a bullet train will repeatedly strike at speed. Building at ground level creates other problems. A wide embankment consumes land and becomes a barrier across local roads, canals, and communities. Every conflict then needs a bridge, tunnel, or diversion. And high-speed rail does not mix politely with level crossings. Raising the railway changes the bargain. A viaduct costs more than an embankment, but concentrates its permanent footprint beneath the piers. Water and local traffic can pass between them, while the loads reach deeper ground. World Bank research on China's high-speed rail program found that viaducts were often preferred specifically to reduce resettlement, protect fertile land, and limit environmental disruption. Contemporary reporting on the Jiangsu section added another advantage. Piles offered tighter control of settlement in the delta's soft soils. So the bridge was not stretched across flat land because engineers had mistaken fields for an ocean. The land itself was the obstacle, and elevation was the solution. But the word pile creates one of the most repeated mistakes in this bridge's story. Online descriptions often place the bridge on roughly 9,500 pilings, without defining what was counted. An official record shows why that matters. In just one 28.188 kilometer section around Suzhou and Yangcheng Lake, the work included 8,742 drilled piles, but only 845 foundation caps and 845 piers. A pile is not the column visible beneath the deck. It is one of several deep foundation elements grouped below a foundation cap. The cap combines their strength. The pier rises from it. Bearings above the pier support the bridge beam. Blurring the categories is like counting every root and announcing that a tree has hundreds of trunks. Those hidden foundations spread the load through a larger, deeper volume of ground. The challenge was not simply preventing sinking, but preventing neighboring supports from moving by different amounts. At high speed, the train, rails, concrete track slabs, bridge beams, bearings, piers, and soil behave as one connected dynamic system. A small error repeated under millions of wheel loads becomes a maintenance problem. A larger error becomes a safety problem. The Beijing-Shanghai project therefore used strict settlement observation before track installation. Designers adjusted foundation layouts and bridge parameters in the soft soil sections while the ground consolidated and the structure gained load. The longest bridge record is visible from a drone. the tolerances that make it usable are mostly buried in mud. Once the foundations were ready, however, China faced a production question almost without precedent. How do you manufacture a bridge on the scale of a regional railway? The answer was to stop treating every span as a unique bridge. Most of the structure uses a standardized language of prestressed concrete box girders. A box girder is hollow inside, which places material where it works hardest while avoiding the weight of a completely solid beam. Steel strands are tensioned so the concrete begins in compression. When trains load the span and try to bend it, that stored compression helps resist the tensile stress that concrete handles poorly. Across China's high-speed rail program, common spans were 24 and 32 meters. World Bank engineers reported typical weights of 750 to 800 tons. On the Beijing section of this railway, a 32-meter beam weighed 900 tons. That is an entire bridge span weighing roughly as much as 600 family cars, and it had to be installed again and again. The solution resembled a moving factory. Temporary casting yards stood beside the route. Multi-axle carriers transported finished girders to launching machines, which positioned them between completed piers before advancing to repeat the cycle. A major contract section from Changzhou east towards Shanghai included 6 girder yards. In the 28-kilometre Yangcheng Lake section alone, crews produced and erected 820 box girders. Across 165 kilometers, a simple division suggests roughly 5,000 standard span lengths, although the real bridge mixes several dimensions and special structures. One crew would have become old and philosophical before reaching Kunshan. Multiple teams and construction fronts advanced in parallel. This is where the bridge's apparent dullness becomes its superpower. Repetition reduced the number of one-off designs, created predictable production, and allowed specialized equipment to keep moving. But then the production line reached places where a standard beam could not fit. The popular story describes one 9-kilometre Yangcheng Lake crossing on 2,000 pillars. The official record is more complicated and more revealing. The documented 28-kilometre section crossed the Yangcheng Lake area 7 separate times, for a combined lake zone distance of 5.9 kilometres. It also crossed 20 named transport routes, including expressways, canals, major roads, and the existing Shanghai-Nanjing Railway. The bridge did not encounter one boss battle. It encountered a queue. Standard girders handled much of the route. Wider roads and navigable waterways demanded longer, continuous beams. The same section included a 96-metre tide arch and a continuous beam and arch structure with a main span of 136 metres. These special structures created clearance where a dense row of ordinary piers would obstruct traffic or navigation. Construction over water added another responsibility. Foundation drilling produced material and slurry that could not be released into the lake. Contemporary reporting described plans to remove it from the worksite. Another popular claim says the bridge can absorb a collision from a 300,000-ton ship. That statement does not appear in the official engineering record. Yangcheng Lake is not a supertanker route. The real design is impressive without importing a ship from somebody else's mega project. It had to thread a high-speed railway across water, roads, and existing rail while preserving clearance below and millimetre-level geometry above. Each special span solved a local problem, but it still had to join the standard viaduct as one continuous route. And after the last beam arrived, the builders still did not have a railway. They had 165 kilometres of extremely well-organised concrete. On top of the beams came the system passengers actually trust, the track. Traditional track sits in crushed stone ballast that distributes load and can be adjusted during maintenance. Danyang Kunshan instead carries CRTS-2 slab track, a ballastless system using prefabricated slabs as a controlled base for the rails. The scale reappears immediately. The official record for the 28-kilometre Yangcheng section lists 8,779 track slabs, each installed, grouted, and finely adjusted. Then there is temperature. The bridge is not one solid concrete bar. Its spans sit on bearings and move under load and seasonal heating, while the rails form a continuously welded surface. Engineers had to control the interaction, so movement did not become a buckle, crack, or change in alignment. The project treated continuously welded, ballastless track on ultra-long viaducts as a major innovation. Dampers reduced vibration and noise, while round track slab restraints lowered resistance as bridge and track interacted. This is a better way to understand claims that the bridge is unshakable. Good bridges are not motionless. Concrete expands. Bearings rotate. Beams deflect.
Foundations respond to the ground. The engineering achievement is to predict those movements, separate the ones that must be allowed from the ones that must be restrained, and keep the rail geometry inside a very small envelope. The full Beijing-Shanghai line went from formal construction launch on April 18, 2008 to commercial opening on June 30, 2011. About 130,000 people worked across the entire 1,318-kilometre railway. When service began, Guinness recognized Danyang Kunshan as the longest bridge in the world. The record was spectacular. The first 15 years of operation were the harder test.
A mega project can win a record on opening day and still fail its purpose over the following decades. This one became part of China's busiest high-speed railway. By June 2026, official operating data showed that the Beijing-Shanghai line had run more than 2.22 million trains and carried over 2.3 billion passenger journeys in 15 years. The fastest scheduled journey between the two terminal cities had fallen to 4 hours and 18 minutes. Those totals belong to the railway, not the bridge alone, but the line needs this elevated section through Jiangsu to separate fast trains from local roads and waterways between Danyang and Kunshan. Its value is not a viewing platform, toll, or tourist attraction. Passengers may never realize when the record-breaking bridge begins. The view repeatedly changes while the deck continues. That anonymity is almost the point. The structure turns a messy sequence of local conflicts, soft ground, farms, canals, expressways, older railways, and urban edges, into one uninterrupted operating surface. It lets the train experience the delta as a line, even though the land below is anything but simple. And after 15 years, the record still belongs to it. Guinness continues to list Danyang Kunshan as the world's longest bridge. The more precise Chinese engineering figure is 164.851 kilometers. That number deserves admiration, but it can also distract from the bridge's most consequential achievement. China did not build a conventional bridge and stretch it until it broke a record. It broke an enormous regional problem into repeatable pieces and made those pieces behave as one machine. The Danyang Kunshan Grand Bridge is not beautiful in the way a suspension bridge is beautiful. There is no single moment when gravity appears to lose an argument. Its drama accumulates quietly. A buried pile transfers load, a pier holds its level, a bearing permits movement, a prestressed girder resists bending, a slab preserves alignment, and a train crosses the result at 350 kilometers per hour. Then the sequence repeats for more than 100 miles. That is why the common myths actually make the project smaller. A vague count of 9,500 pilings erases the difference between deep foundations and visible piers. A single 9-kilometre lake crossing erases the 7 water crossings and dozens of roads, canals, and rail conflicts. A giant ship collision turns precise delta engineering into an action film. The authentic story is an industrial one. It begins with spending more on elevation, so less land is divided. It continues through foundations in soft soil, casting yards that made spans repeatable, special arches where the standard system opened, and ballastless track adjusted across a structure with its own weather. The result does not conquer one river. It negotiates with an entire landscape. And every ordinary journey is another proof test. Not a ceremonial convoy of trucks parked for cameras, but train after train crossing until the world record becomes part of the timetable. For more stories that look beyond the headline number, subscribe to Mega Projects. And consider the real choice this bridge presents. Which is more impressive, one spectacular span that forces the world to look up, or 5,000 mostly ordinary spans engineered so precisely that passengers barely need to look down?